Hello, my name is Eric Norman, and our first topic to discuss is type and characteristics of machine instructions. First, we need to explain the meaning of machine instructions. So, machine instructions are the basic commands that a computer processor can understand. They are the lowest level of instructions that can be directly executed by the hardware. And the type of machine instructions, one is number one is arithmetic and logical instructions, and or XOR on data. Number two is data transfer instructions. These instructions move data between memories and registers, or between different registers. And number three is input and output instructions. These instructions enable communication between the processor and an input or output device, such as the keyboard display. And number three is load and store instructions. These instructions are used to transfer data between memory and registers. So now we are moving on to the characteristics of machine instructions. These include fixed length. Each machine instruction is typically of fixed length, which specify the decoding process of the hardware. And the second one is the binary presentation. Machine instructions are represented in binary format.
My name is Success Joy Likem Hypo, and I am here to introduce you on the topic instruction addressing modes. As my earlier colleague introduced you to the topic, which has to do with types and characteristics of machine instructions, I'll be taking it from here for us to learn more on the topic. First of all, when we talk about instruction addressing modes, we could say that it refers to the process used by a microprocessor to deliver instructions to a machine so that we can perform an operation, right? So again, we could say that the addressing mode is a method to specify the operands of an instruction, and the job of the microprocessor to execute a set of instructions that are stored on its memory so that it can perform a specific task. And these operations require the following. The first one has to do with the operator, which determines what will be done, and the second option has to do with the operands which are involved, or which defines the data to be used in the operation. For example, if we are to add two numbers, that is a number 1 and another number which is 2, we are adding these two numbers. We could say that mathematically we write it as 1 plus 2, and in this case our operator becomes what? The addition operator sign, and our operands become the numbers 1 and 2. Alright, so from here we would move to the types of addressing modes. Okay, so there are a lot of types of addressing modes, but taking into consideration few, which are mostly the 5 main ones, we would look at the first one, which has to do with what? the immediate mode. And with the immediate mode, the actual data to be used as the operand is included in the instruction itself. So the actual data to be used is included in the instruction itself. So we could say that if we want to store an operand 1 into a register and then add another operand to it, with the immediate mode, the data values 1 and then the 2 would be part of what the instruction in which we are executing into the microprocessor. And if we could see on our screen, this is a graphical representation of immediate addressing mode. Okay, so moving to the second one, we are talking about the direct addressing mode. And with the direct addressing mode, the address of the operand is specified in the instruction. It's just as we should look at this very well, because with the immediate instruction addressing mode, we say that the operands are also included in the instruction. Here we can see that the instructions are also included, but the only difference that has to do with this one is the processor is the one responsible for retrieving the actual data directly. So the processor in the direct mode, the address of the operand is specified in the instruction, and the processor will retrieve the actual data directly from the address specified into the instruction. Again, we'll move to the indirect mode, and before we move to the indirect mode, here is also another graphical representation of how the operation is performed in the direct mode. Okay, moving to the third one, which has to do with the indirect mode. With the indirect mode, the operand value is stored at a memory address that is specified indirectly. Let's look at the word that it said what? It is stored at a memory address that is specified indirectly. So with that, we could say that an instruction might load the value from the memory address store into a register, into another register. This place, the location for data collection is not specified, so meaning we can move from one set of register to another set of register in search of what our instructions. That is how it is being performed. And for the fourth one, we are going to the register addressing mode. And with the register addressing mode, the register addressing mode indicates the data stored in the register itself. It indicates the data stored in the register itself. That is all it has to do with it. So the instruction contains the address of the register. The data would be retrieved from the register. And we'll move to okay, so that is with the register addressing mode. And after all this that has to do with the instruction addressing mode, we should take one key thing into consideration that has to do with different processors may support different addressing modes, and some processors may have additional addressing modes specified to their architecture depending on the nature of the machine or the way in which the machine is built, and depending on the processor. Then we could say the types of addressing mode it would support in this case. That is what the statement means. So that is all we have to do with the instruction addressing mode. Sorry. Thank you very much. I'll be treating on the topic that has to do with the scalar processing. Okay, so with the scalar processing, we could say the scalar processing refers to the execution of a single data item that is being instructed at a time. Even when we look at the term scalar processing, when we take the word scalar, it has to do with what? A constant. So meaning one thing at a time. That is what it's saying. And over here, instructions operate on single values such as integers or floating point numbers. And the scalar processor retrieves values, perform operations, and store results. That is what the scalar processing does. And secondly, the scalar processing is contrary, or in other words, we can say in contrast to vector processing, with the vector processing instruction which operates on multiple data items. Again, we could say single instructions can be performed. Again, single instructions can perform the same operation on multiple elements of a vector. Going on again, we can talk about the scalar processing as a processor does not have a specialized hardware for vector operations. This is also used when the amount of data being processed is small or does not justify the overhead of the vectorization. And to end this part of our presentation on scalar processing, there are also things we need to take into consideration before my other colleague takes over. And that is, we have to know that in scalar processing mode, mode still applies. The choice of addressing mode determines how the processor accesses operand values for each instruction. Okay, so thank you for your time with me, and my colleague would take it from here. Thank you very much.
Hello, I'm David Kwasi, presenting performance instruction pipelining for Bouvet computer architecture. Our first point is instruction pipelining is a technique used in scalar processors to improve performance. It involves breaking down the execution of instructions into smaller stages and allowing multiple instructions to be processed simultaneously in different stages of the pipeline. This can help reduce the overall execution time of a program by overlapping the execution of multiple instructions. Now, the second point is each start each stage of the pipeline performs a specific operation, such as fetching the instruction, decoding it, executing it, and storing the result. As one instruction moves from one stage to the next instruction can enter the pipeline and begin its execution. This allows for a continuous flow of instructions through the pipeline, increasing the overall throughput of the processor. However, instruction pipeline also introduces some challenges, such as dependency hazards and branch hazards. Dependency hazards occur when an instruction depends on the result of a previous instruction that has not yet completed. Branch hazards occur when there is a conditional branch instruction that could change the flow of execution, causing a potential delay in the pipeline. To mitigate these hazards, techniques such as forwarding and branch prediction can be used. Forwarding allows the result of an execution to be forwarded directly to subsequent instructions that depend on it, avoiding the need to wait for the instruction for the result to be stored in the memory. Branch prediction involves predicting the outcome of a conditional branch instruction before it is actually executed, allowing the pipeline to continue processing instructions without waiting for the branch to be resolved. Overall, instruction pipelining is a key technique used in scalar processing to improve performance by allowing for